Good morning and welcome to this course on distribution theory and Sobolev spaces. It is a first part of PDE course, advanced PDE course, part 1, and you have already seen some preliminaries about some analysis mainly on LP spaces and some Fourier transform convolutions, and a little bit you may see about that it more later. And you also seen the modifiers and how do you get the approximations in LP functions by smooth functions, etc. So we continue that preliminaries here, and in this three or four lectures, maybe 3 lecture, we will introduce some important spaces and which we make it a topological space. So you would have seen already inner product spaces, non-linear spaces, metric spaces, but many of the interesting spaces do not come under that category. In other words, you will not be able to generate a topology using such norms. You will not be able to give a natural norm there. So there is another class of topological vector spaces known as locally convex topological spaces. So we will introduce this concept of locally convex topological spaces, and you will see the importance of such a locally convex. One of the advantages is that whenever you define a space, it is important that you should be able to define continuous linear functionals on that space with a continuity with respect to that topological spaces. In general, metric spaces, so that may not provide that one, and but locally convex topological spaces provides a non-empty dual. So in many spaces we may not know how to naturally define norms or thing. We will see start with the motivating examples. So topological vector spaces, topological. So that is a topic or study for the next 2-3 lecture. Topological vector. Vector, or we also call it linear spaces. Okay, so that is a discussion. More specifically, you will be calling it so maybe a shortcut TLS, topological linear spaces, or more specifically special locally convex topological linear space, okay, LCTLS, instead of writing all the time. So that is what we are going to introduce here. As I said, if you have seen many metric spaces, for example LP spaces, LP for 1 less than or equal to p less than or equal to infinity, these are all Banach spaces. Okay, that means Banach space means there is a norm, there is a norm which it generates the topology, right. So it is a topological vector space because it is a vector space, and then there is a, we will give the precise definitions soon, and these are so it is a topology. Of course any norm linear space is also a metric space, but when you take LP for 0 less than p less than 1, you can define I am not going to do that, but you can look into the book, can define a metric, but if you look at its dual for this one is an empty set. So probably you can see reference Rudin, this example is given there, of course Rudin function analysis book. So you see it is a matrix, there are matrix, that is why. So if a space does not generate any dual, that means if you can't define a continuous linear functional on that, then that space indeed not useful, because the dual is one of the important thing on this space, because that is how you get operators and your solutions are converted into that one. So this concept of locally convex is precisely to address, and many problems you can do only with locally convex. So, let us start with the now thing. So, let us start with your some of the familiar spaces. So, I am going to recall most of the spaces. So, the LP spaces you are already introduced, okay. That is some sort of an integrable spaces. So, there are also smooth spaces. So, you have two types of, one is smooth class of functions and the other one is the integral class of functions. Integral class of functions are the LP spaces, and which you will see more about LP and other Sobolev spaces in the way of integrable spaces. But the smooth spaces are also, you know, that suppose AB. So, let me recall everything once more. These are all functions defined on AB, you see, AB to R. Of course, you can define C or any other thing, continuous, okay. This is on a closed interval AB. AB is a closed interval, and this is also sometimes denoted by C naught. You will see why that is denoted, because we will define more the thing. So, on this you can define a norm which we denote by norm at 0, that is supremum of modulus of f of t, where t is in AB. Since AB is a closed interval and f is a continuous function, this is a finite quantity. So, C AB with this norm is a Banach space. Okay. So, you can so now consider the next step is to consider C1 of AB. That is a set of all f in C of AB such that your derivative is also in C of AB. So, naturally this is contained in C of AB. So, the norm on C of AB can be used to define a norm on C1 of AB. So, indeed norm is a norm on C1, but it is not complete, but it is not complete. This is some message you have to understand complete. The message is that, the reason is that if you choose Fn in C1, Fn's are continuous and also differentiable, which is derivative is continuous, and Fn converges to f, Fn minus f goes to 0, then this only gives you subconvergence. It is a uniform convergence basically. So, it gives you the uniform convergence of Fn to f, leading to this will imply indeed f is in C of AB. That is why C of AB you get complete, but it does not give you anything, does not imply anything about f prime, about f prime. You do not even know that f prime. The reason, that is a message, it is a general thing. So, Fn's are differentiable, but it is not somehow embedded in your norm. So, if the norm does not carry the property of Fn, that property will not be reflected in your limit process. That is how most of the time incompleteness happens, because when you do the topological convergence, that convergence should have somehow defined in terms of the various properties. So, the property of Fn are differentiability. So, somehow you have to incorporate that differentiability concept. This is always, so whenever you have to have complete space, all the properties of that space, which are defining properties of that space, should somehow embed in your norm or whatever way you are defining the topological space to recover it in the limit. Okay, that is a general message. So, how do you do? So, on C1, so what you do is that you define a norm f at 1 is equal to norm f at 0 plus norm f prime at 0. So, you have a norm, and with this C1 is complete, you see. So, that is what you have to do it. So, we will go to the so this message you keep it in mind. If you want to get a complete space, somehow you have to incorporate in a proper way. Okay. So, so this way you can do very general any CM general. So, you can consider CM, M is an integer for M is in N. You can define this is M times differentiable functions, and the mth derivative is also continuous. So, you know these spaces already. So, how do you define a norm there? So, you define a norm f at M, can define this way. You can summate norm of f all the derivatives. So, you define all the jth derivatives and you do it where j is equal to 0 to m. So, Cm of AB norm M is complete. Okay. So, now this immediately, so you can generalize this not just for R, you can do it for Rn. So, if K is a compact set in compact, so not in Rn, is in Rn compact, then you can define Cm and Cm of K, you can do M times for all its derivatives, and then you can define norm f at M is equal to all the derivatives you take it d power alpha of f and derive the supernorm. This is a supernorm. So, to make the space clear, I may write it. So, I will use both the notations just like here M, and if it is necessary to represent K, I will also mention K. Sometimes it is necessary, and this is finite. So, this is for all mod alpha less than or equal to M, and you know that d alpha f is equal to where d alpha of f is equal to d power mod alpha of f by dx1 power alpha 1, since this is the first alpha n. This is already introduced somewhere, or you would have learned it earlier also, alpha 1 plus etc. alpha n. This alpha is called a multi-index, okay, where alpha 1 is equal to alpha n multi-index and where alpha I is a non-negative integer, you can take the 0 value. So, you have all this if you are not you do not want to recall, and because of this because M is a K is a compact set, this is a finite quantity. Okay. So, this is basically what it says, that norm f at mk M is nothing but summation. So, what do you say, supremum x is, I am rewriting once because if you are not comfortable yet, modulus of d mod alpha of f of x by all this dx1 alpha 1 etc. dxn alpha. Okay. So, you do this thing. Okay. So, the question is that is the questions now you are going to ask. So, whenever you have a compact set you can do that one. So, now what do we do? The questions. One, what do we do if you want to consider C infinity even with a compact set? The thing is that f in C infinity is differentiable, all derivatives x's are differentiable. Indeed, no mem for every k defines there, and it defines a topology on AB. So, naturally, but for if once you fix m, it will only take care of the derivatives of order up to m. But how do we carry out, how do we incorporate all the derivative? The same thing, and now I cannot do it summation or even the supremum, because now the supremums are for infinitely many things if you have it. Okay. So, how do we carry out, how do we incorporate all the derivatives in the definition of C infinity? Okay. You have to somehow incorporate the above method, you cannot immediately do it. So, you need a different way of approaching it. The other things, this is for 1. So, the same thing, what about if it is an open set? What about even C not of open interval AB? What do you do? Because on C naught the supranorm is finite, norm F naught need not be finite, that is the problem on an open interval. Okay. And more generally, how do we define Cm of omega where omega open in Rn? Okay. And with both the difficulties, how do you define C infinity of omega? Okay. So, there is also another space which is one of the most important space called test function space. We incorporate one more property, that is C infinity of omega. So, you have the difficulty one, this is open, we do not know how to handle. You have infinity, you have other question. Now, the third one is compactness. So, this is nothing but set of all f in C infinity of omega such that support of f is compact. So, you have to, if you want to get a complete space, this compactness nature also has to be somehow incorporated in your topology. Okay. So, what we are going to do, we are going to define topological spaces, two ways define topological spaces via seminomes. Okay. So, let me try to get some motivation for that. So, probably before going to that, so let me summarize what we are going to do for everything, and then we will get into the other things little more about it, seminomes, definitions, etc. So, let us try to understand. So, you have studied the inner product space. So, this is a diagram of all your spaces. Okay. So, you have inner product spaces, right. So, you have inner products. So, you see we call it say inner product space, and then if you add completeness, that will be your Hilbert space. So, a typical example is L2 and any Rn. Okay, we can have. So, less general is your normed linear spaces, normed linear space. Of course, there is a vector space structure together with a topological space. So, you have normally and if you add complete, you get your Banach space. Okay. So, a typical spaces are your LP spaces, 1 less than or equal to P less than or equal to. Of course, P equal to 2 you get inner product space, but then P not equal to 2 it is only a normed linear space, of course. So, every inner product space is a normed linear space, but normed linear spaces are not that way. And then you have a typical generalization which you have seen is your metric spaces. There are many metric spaces. Okay. So, you can define a metric on it. Okay. It is not necessarily a typical there are thing one I already introduced LP. So, rho less than P less than. You will see more about it some of our thing. So, this is a more general. So, the metric spaces need not be non-linear spaces. Okay. The other one which you some of you probably may not have seen and which is the topic of discussion of these things is so called locally convex topological spaces, and also the class of them are given by semi-normed linear spaces. These are semi-normed linear spaces. Okay. Also it will give you semi-normed linear, and combined all that you have your the class of topological vector spaces. Topological vector spaces. Okay. And this is where our interesting spaces going to be, where you will see your Cm of omega, you will also see C infinity of omega, you will see Cc infinity of omega and all that, and you will also see the duals are non-empty. That is not guaranteed for other spaces. So, you will get that. Of course, if you have one last comment on this general thing, locally convex topological linear space plus if you do metrizable with some invariant metric and all that, okay, plus completeness, complete, you call it a Frechet space. Okay. Frechet space. Okay. Of course, there may be not that this is completely disjoint. So, if the kind of semi norms are given by a countable family, you will be able to define a metric to make it a complete it is a metrizable space. So, you will get a locally convex space which are metrizable. The interesting thing is that these two spaces which we define will be metrizable, but the topology which we are given here need not be metrizable. Of course, we will also see you can indeed define another topology which is metrizable on this space, but it will be incomplete. So, we want completeness all the time, and then you lose metrizable, but except that you get almost everything. Okay. So, this is basically the kind of structure of all the space. Of course, much more general is topology. So, from here you will have topological spaces. Topological spaces, there need not be a vector space structure. Of course, so there will not be any algebra. So, it is just a topology. Okay. The interesting things are topological vector spaces, and these are the special cases in the above, because you have a vector space structure, topology, and the somehow defining that one. So, another I have some 5-6 minutes, I may just give you some definitions today. And so, definition, okay. So, a topological space X, topological space X is a set together with a topology. I am not going to define what a topology is, you know that is a collection of subsets satisfying certain property together with a topology. Topology, you know, no need of vector space structure. Okay. So, the next definition, a topological vector space, it is also called it as linear space, because that is a linear structure. Linear space X is a vector space together with a topology, and there should be some connection between these two, together with a topology. So, it is a topological space first of all, and there is a linear topology such that the operations, algebraic operations, such that the algebraic operations one, what are the operations, x y, this is from x cross x to x. Okay, topology means you can define it 2x plus y in x to alpha x. This will be from the vector space, which is so every topological space is defined over a scalar field. Okay, this is the scalar field. It may be complex or any other field. Okay, so we will, since we are only restricting to the real line, we write it so need not be. So the moment you are defining a vector space, there is an underlying field. Okay, so it will be a vector space on that field, and your algebraic operations. So this going to alpha x. This is the point. This is in x, and third one x in x going to minus x in x. All these three operations are continuous. So that is what you are defining topological space. So you have plenty of examples, you have already seen the topological spaces, all the spaces which I have defined earlier. So only thing, certain topologies, all these things you are not yet seen much, probably maybe you have seen it also, but you have plenty of examples. You can define many examples here at this stage. You have defined topological vector spaces. Okay, so it is not that you don't. So the next job, I will just give a definition of that. We will not study very general topological vector spaces. We study a special class namely semi-normed linear semi-normed linear spaces which are topological vector spaces, semi-normed linear spaces or locally convex. I will give you the definitions soon, maybe in the next class. Locally convex topological linear spaces. Okay, so we think so. One last definition today, and then in the next class we will immediately continue in the next class. So, the definition of a semi-norm and examples will be given later. Okay. Let X be a linear space, X be a linear space. Okay. A semi-norm P on X is a mapping P from X to R satisfying one P of X plus Y is less than or equal to P X plus P Y for all X Y belongs to X. 2 P of alpha X is equal to modulus of alpha into P of X for all X in X and alpha in R. Okay. So, such a, and this one is called the sub-additivity. Okay. Sub is not additive, we are only sub-additivity, and you also call triangle inequality if you want, triangle inequality. So, what is the difference of a norm from this one? So, trivially, so this is that trivially you may, if you are not convinced, check it. P of 0 is equal to 0, right. P of 0 is equal to 0 and P x, if you do not see that one, you see that P x greater than or equal to 0 and modulus of P x minus P y is less than or equal to P of, because P is always positive. So, you do not need to write modulus of P, this is true. Okay. So, what is the difference is the here P 0 is equal to 0, that is true, but P x equal to 0 need not imply, that is a difference. This is a very crucial property. You may quite often in a norm take that norm x equal to 0 if and only if x equal to 0. That is not in general. P x need not imply x equal to 0, because why it is crucial that non-trivial x lead to P x equal to 0. Okay. So, non-trivial x non-trivial elements goes to 0, and that can create problems. Okay. And that is what exactly you are going to see. So, you will see semi-norms soon to define. So, I will stop the lecture here and we will continue with the semi-norm linear spaces. Thank you.